Ma'am, is it okay now?
Ma'am, is it okay now?
Yes, ma'am. A great pleasure to welcome our chief guest, Mr. Deepan Raj, and all of you this morning to the ATAL Academy sponsored FDP on Intelligent Computing in Data Science, which is organized by SKCET Coimbatore. It is gratifying to note that the agenda of the seminar covers a wide range of very interesting items which is related to the power of data and mind and computer vision perspective. I have a very pleasant duty of introducing our chief guest, Mr. Deepan Raj. He is a very well-known and one of the most distinguished scientists. Where he did his UG in Agni College of Technology, then he did his ME in MIT. Now he working as an embedded software engineer dealing with artificial intelligence solution tools for automating the validation process in automated driver information, HUD, and infotainment systems at Visteon Technical Service Center. And he conducted 300 plus workshops, 6 plus training programs, then 4 plus corporate trainings. For his pioneering work, he has received appreciation from the former President of India, Dr. APJ Abdul Kalam, for creating a 5-feet cost-effective humanoid robot. Then he received an international award for contributing a real-time project using robots for easing the work of farmer in the farm fields, which is held at Tuticorin. Also, he received an award for contributing a novel approach in effective brain-computer interface by coining a never-before concept named Neural Linguistic Dictionary. He also awarded the most impressive project of the year in IIT Kharagpur for ISRO Mars Rover Challenge. He won 25 plus technical. He published more than 5 papers in reputed journals. He has conducted 100 plus workshops. No. Okay. Thank you, sir. I will hand over the session to Mr. Deepan Raj. Thank you, sir.
Thank you, ma'am. Thank you so much. So, yes, let me share my screen first. Okay. Yes, like today we'll be like focusing more on the sequential based input, that is going to be our NLP and other sequential data, like probably going for sound processing and other stuffs. So, but our main agenda is to understand the RNN and the concepts behind those. I mean, concept behind RNN like LSTM, GRU, and attention models and stuffs. So we'll go, slide by slide to understand like why do we need an RNN while we have this classic multi-layer perceptron and convolution neural networks and all of the stuffs. So as we already know that feed-forward network is one of the best network which you can ever get, and yes, we can do a lot of great applications using that bit. So light from the autonomous cars, a lot of application which I can count on feed-forward network. Yes, because it can able to process that particular task in that particular time. So I mean, if the if the data is given at the present time, I mean the output will be processed for that particular present data and will give us the great output. But the problem behind this feed forward network is like it doesn't have any memory unit, so that it cannot able to understand, or it cannot able to correlate the data which is already been passed to the network, like previous data to the, or some other data which has already been passed there. So I mean, the decisions are made only to the current input, and there is no like connection between the current and the past inputs. Okay, so that is one of the major drawback of the feed forward network. But yes, I cannot say it as a drawback, but I mean, it has done its job in doing a lot of great I mean works for us. So in order to substitute this kind of a problem, in order to address this kind of a sequential problem, we enter into another type of a neural network known as recurrent neural network. Because I mean, in a recurrent neural network, we could able to handle a sequential data. Let's say, I mean, we could able to handle a sequential data, I mean, at a easier manner, and also we can able to understand what is the previous data and how do I correlate with the present data. So we could give an analogy, something like that. So let's say, I mean, I can tell you, like, let's say we are having a conversation right now. So you cannot come to a conclusion that, I mean, what kind of discussion we have made without I mean closing the particular argument, right? So let's say I am a good boy. So if I say only just I am a good, so I can able to even expand that conversation to a different subject, right? So obviously, without understanding the entire context of my conversation, so it is very difficult to understand, or very difficult to give a correlation of what kind of data we are handling and what kind of output have to be given for that particular input. So when this is the biggest drawback when it comes to, I mean, feed forward network, and this particular drawback can be addressed using recurrent neural network. So it has a memory unit that can able to somehow store the data, so that if the present data comes into play, I mean, we could able to correlate with the past data. Okay, so we'll enter into some of the use cases and some of the application which RNN can actually do, because people think like when we say about RNN, they just say, okay, we can do natural language processing stuff, we can do chatbots. Yes, that is also a part of this recurrent neural network, but yes, there are even much more things which recurrent neural network can do, because it is equally important as feed forward network and also your convolution neural network. So one such application, one such thing which I can say is like image captioning. So in image captioning, it can able to, I mean, let's say we can able to give one input, so that's going to be our image. So in that one input, we can able to generate multiple outputs. So let's say it's going to give us a caption for a particular image. So I mean, let's say a football player is playing a football. Okay, I mean, a player is playing a soccer. So that's going to be the output when I give an image with the player standing with the football in a football jersey. Okay, so obviously, just one input is given as a given as the prime state for this particular neural network. So we'll be getting multiple outputs in the form of text as the output. Okay, so this is one such application or one such ideology where we can able to process one to many. So one input and many outputs. Okay, so that's one thing. The second thing which I can say is sentimental analysis. So I mean, sentimental analysis is like, let's say, I mean, you have a review in your Amazon or Flipkart or whatever it may be, even movie reviews, right? So, I mean, obviously the review will not be in the form of one word. So obviously it will have multiple words in the form of sentence. So by reading those multiple words, my neural network should able to understand whether the given review is positive or not. So it's going to be yes or no, right? So obviously it's going to be many to one strategy. So this is also I mean, one of the great applications which we can make using recurrent neural networks. So I could always say that, I mean, this sentimental analysis was one of the stepping stone for recurrent neural network, where we got a lot of attention. Like, what are the things which we can do using recurrent neural network when it can able to handle sequential data. Okay, so that's another thing. So, and also we do have this machine translation, right? So let's say we are using this Google Translate for a long time, right? So I mean, we can convert any language from let's say from English to Tamil, or Tamil to English, or English to Arabic, whatsoever. So we could able to process, we can able to translate any kind of a language which is given to it. So this is also, it's possible, it's all because of recurrent neural network. So where we can even do this many to many translation, where I mean, the many words, I mean, the words which you are trying to translate will be processed, and somehow, I mean, we'll be getting the output, I mean, as the, I mean, output language. So it's like going to be, sorry for that. So it's going to be like many to many translation. Okay, so let's say, I mean, I can give any input, and the output will be in the form of a different language. So that is also possible. And I believe that, I'm not sure how many of saw this recent feature in Facebook, where even people who talks Tamil or some other language in English, let's say, I mean, we do type our language, our native language in English, right? So that since we can't able to type I mean, the exact words in our keypad, because since we have only English keypad in our mobile phones, we'll be like typing this our native language in English itself, right? So Facebook has even created a application, deployed a feature that can able to even translate that kind of I mean that kind of a sentence which you are given. So let's say you talk in Tamil with English words, so obviously Facebook will translate and give it in the give the meaning in English. So that is also a major breakthrough which Facebook have done, and there's a lot of improvement is also going. So if you haven't watched that, just go to your feeds and just see for some Tanglish words or some other, I mean, languages words, and you can see some translation right below it. Okay, so that's also one of the major improvement which is really happening right now in the recurrent neural network phase. And also we already know that this attention model, let's say, your video classification, let's say activity recognition, all those stuffs can be done using the RNN. So where multiple video frames will be given to the neural network. So initially, I mean, we cannot like do with just recurrent neural network. Obviously, we will be using CNN to detect or like classify or to understand what kind of image is that, and frame by frame CNN will be giving some ideology like what kind of frames are this. So based on those, words, I mean, the output of the CNN will be correlated by the recurrent neural network to understand, okay, what kind of scene it is, because we can't, I mean, give a comment by just understanding one scene, because things might change if people are running or like walking, right? So when you see a person who's in a jersey, like in a, like, what is it, athletic jersey, so definitely we'll be saying that he's going to run. But what if he's like going for a long walk? So obviously the activity will be different when it comes to a video based classification. So even to understand that kind of a concepts, recurrent neural network will be the right candidate to be approached. So these are one of the many ideologies and applications which can be done using recurrent neural network. So we'll get into details about what is RNN, so what are the components inside it, so that we could even go further and say the hands-on part. Okay, so this is what RNN will look like. So generally, when it comes to a normal multi-layer perceptron, it's going to be like input, hidden layers, and going to be output, right? So it's going to be something like this. So it's going to go something like this. But in RNN, we'll be having it can able to handle sequential data, so that let's say I have like multiple input. Let's say recurrent neural network is going to be an input. So this three data will be pushed to the each and every neural network like this, something like this. So obviously the data will be like passed from one to another, and finally like we'll be getting intermediate output for each and every one, and finally we'll be getting one such output. Like, let's say if it is one to many or many to one, whatever the situation it might be, so based on that the recurrent will try to give you the output. So we'll somehow unravel what is the actual component inside the RNN. So this is the actual formula, or like this is the like actual inference of a recurrent neural network. So basically, for a normal feed forward neural network, we'll be having the function vector, which is going to be having the activation function weight of it. So that's going to just handle with the present data like xt, that's it, right? So this is the feed forward network. But in recurrent neural network, we will also be considering the old state, okay, the past state of the neural network. Okay, so let's say h of t minus 1 is the past state, and x of t is the current input. F of w is going to be some, it's going to be the activation function and the weight weight which has been distributed for it. Okay, so finally we'll be getting the new state h of t. So let's unravel it much more in detail. So let's say, as I told you, this fw can be like we'll be having two things here. One is like the activation function, which is going to be tan h, and the weight of that particular neuron. Okay, so let's say we'll be also having the weight for input the present data into the past data, and finally we'll be getting the answer for it, and we'll be finding the y of t, which is also having a weight, a separate weight, and the separate state h of t. Okay, h of t is going to be divided from here, and finally we'll be getting this h of t weight of the particular output. Okay, so this is how a recurrent neural network is being formed, and this is the actual ideology, or the actual concept behind recurrent neural network. So it doesn't handle only the present data, it handles the past data as well to give a predicament. So typically here you can see there are like many activation functions which is present, right? So we have ReLU, we have step function, sigmoid, softmax. There are like multiple activation function which you can state down, but I specifically given here is as tan h. So there is a reason behind it. For why we are using TANH. We will discuss about that in the later part of the session. But for now, the TANH is going to be one of the important activation function for recurrent neural network. So likewise, when we go for CNN, you know that ReLU is going to be one of the best activation function, right? One of the preferred activation functions is going to be rectified linear unit. But for recurrent neural network, TANH is going to be the preferred activation function. Okay, so that's one thing. And yes, now let us understand, because obviously it is going to be a little different from the classic feed forward network or your CNN. How this weights have been distributed, how the data is going to be calculated, how I'm going to calculate the loss function, how I'm going to back propagate and update the weights again and again. So these are the confusions which we have in our mind, because as I told you, we are going to handle data in a sequential manner. So here you can see this is how the data is being handled. So let's say this is going to be three words. Let's say recurrent neural network. So I have three data. Okay, so all these three data is like handled sequentially here. So this h of 0 is going to be the past state. Okay, the past state is nothing will be there, so it's going to be 0 obviously. Okay, so if nothing is there, so I'm going to give the past state and I'm going to combine the present state. Okay, and I'm going to distribute a normalized weight function for all the neuron. Okay, so let's say in the initial standpoint, we won't be like giving any bias to the weight. Okay, so we'll be having this normally distributed or maybe uniformly distributed weight function for all the states. Okay, so obviously it's going to be the same for all the input neurons. So it's not going to be different for each and every states. Okay, so it's going to be commonly distributed to all the guys. Okay, so let's say, so now I have also distributed the weights. So for this particular thing, we'll be calculating the h1 state. Okay, so h1 state will be calculated. Based on that, I can able to get the output y1, right? So the output can be derived from maybe somewhere here, right? So the y can be directed somewhere like this. So obviously we'll be like getting getting intermediate output also to understand the deviation, or like where we are actually going to reach the final standpoint. Okay, so that is how we'll be like dealing here. So the first point is like we'll be like pushing the past data and the present data, and we'll be equally distributing the weight function. We'll be like equally distributing the weight function to all the neurons. So the next stage, as I told you, once the intermediate state is found, we'll be like giving the output. We'll be like calculating the output, and we'll be calculating the loss function for each and every intermediate state. Okay, so this is very, very crucial here, because this is where we can able to understand whether the actual learning is happening or not. Because if let's say this y1, the loss function 1 is like very, very less. Okay, so let's say it doesn't learn anything. So I cannot like couple this particular learning rate to this L2, because this might even lead to a better situation, because obviously since it has learned nothing, obviously it might force the next parameter to learn nothing. So obviously the error rate distribution, the error rate calculation will be very, very less, like in the form of 0.001. So which forces the neural network to not update the weight at all. So obviously it might cause even a danger thing. Let's say it will explode the gradient value, so that the global minima, let's say, okay, let's say the global minima suddenly drops like this. Okay, so suddenly drop like this to some point. Let's say it is very confident that we have received like 99% of accuracy without even learning a single data. So even we have this particular kind of a problem when it comes to recurrent neural network. So we'll deal those things. We'll try to mitigate those problems in the later part of the session. But anyways, this is one such problem which people faced when they were trying to formulate this recurrent neural network. So what we did is like so all the intermediary state has been calculated, and all the loss functions also calculated to find the final loss function, rather finding the loss function at the end of the state. Okay, so in this way we might be having a control, or we may be like having an ideology like where this problem happened. So why intermediate state output and the loss function is calculated for each and every step. And finally we'll be calculating the loss function for each and every by like averaging, like cumulatively averaging this all the loss function. So finally the loss function will be calculated, And then once the loss function is calculated, the error rate will be defined. So using the error rate, I'm going to back propagate. I'm going to like back propagate like this, and I'm going to update the weights for each and everything. So and finally, once the weights are updated, I'm going to like calculate the entire weight, and I'm going to equally distribute that particular weight to all the other neurons in the next iteration. So this is how a recurrent neural network is being computed, I mean, on a real-time node. Okay, so I mean, to summarize things up, we'll be like processing data, and we'll be having some intermediary output with the loss functions. So based on that, we'll be calculating the entire loss function, and I'm going to back propagate again to, I mean, update the weights and find the average weight for the entire neural network. So the next iteration, this weight will be used for all the other neurons. Okay, so this is the actual ideology behind the RNN. I mean, okay. So as I was saying, there are like few problems which will occur. I mean, when it comes to, I mean, recurrent neural network, one such thing is like exploding gradients and vanishing gradients. So exploding gradient, I mean, gradients is like, as I told you, it will be like something like this. So I mean, the learning rate will suddenly drop to some point. Okay, somewhere like let's say like in a very minimal epoch, let's say 1 or 2 epochs, I'll be getting 99% of accuracy, and nothing will go, I mean, beyond that. So I will constantly maintaining this 99% accuracy. So if you're getting something like that, definitely we need to be, I mean, make sure that whether we have a good data set in our hand, because yes, data set can also contribute this to this kind of a learning, but we need to also make sure we have a validation set. Okay, so without validation set, we cannot able to understand, or we cannot able to correlate whether it's actually learning something or not. So these are things which we need to take care before giving a comment on the accuracy which we have got. So in order to, I mean, rectify these exploding gradients, we could go for a truncated back propagation. So as I was saying, I mean, in the previous example, if I back propagate here, okay, so on a, I mean, on a neuron by neuron basis, it might even make me a great problem. So what we can do is we can go for a truncated back propagation, where we, I mean, calculate the weight function for this part, this two part of the neurons, and we will average the weight here. And finally, we'll use this weight and go here and truncatively like again update the weights. So it's like going to be like a batch by batch weight updation technique, so that I mean, it might even reduce the, I mean, process of exploding gradients. So making sure the right weights are being updated, because one single wrong weight is updated in the last part, maybe in the first part, let's say this area, this FW. Okay, if one single weight is wrong, obviously it might shoot up the I mean, learning rate, and that might go for an exploding, I mean, gradient. Okay, so that's one important point which you know take care. And then the second thing is like vanishing gradient. So where I mean, nothing will be there to learn. So let's say, I mean, it will be staying at maybe like at some error rate like 90 or something like that. So it won't increase or won't decrease at all. So it'll be like going constantly, like I mean, somewhere without reaching to the global minima. Okay, so because of that, I mean, the vanishing gradient will occur, because there is no point in learning, because it sees like, I mean, I have saturated the entire data set. So no matter how many epoch you run with me, I can't give you any result, because I have nothing to learn from there. So that is also a great problem. It is all because of the activation function onto the memory blocks. So which can be, I mean, which can be mitigated using the activation function tan h, and also by using the LSTM and GRU, I mean, concepts inside it. Okay, so these are the important gradient problem which you will be getting when it comes to recurrent neural network. So even though when you use your Adam optimizer or RMS prop, or like, I mean, your stochastic gradient descent, so no matter what kind of gradient descent you use, I mean, definitely when it comes to RNN, these problem will occurs for sure, because it is actually handling data on a sequential basis. So maybe one set of data might be good and one set of data might be bad. So because of that, this exploding and vanishing gradient will be a major problem when it comes to recurrent neural network. So as I was saying that, I mean, yes, recurrent neural network can be I mean, mitigated by using LSTM and GRUs. So that's what we are going to see right now. So before going there, I'm just showing you a small GIF of what will happen when we don't have a tan h activation function. Okay, let's say we have a sigmoid in the top, okay, and tan h at the bottom. So let's say, I mean, you can see the final value we got is 405, right? But in this case, the initial value is 5. So it's slowly like I mean, being exploding, I mean, again and again to a bigger value. And here in this case, it is like maintaining the value inside 1, because we know that, okay, okay, in this case, yes, we know that tan h is having this operation. Let's say it's going to like, I mean, distribute from -1 to +1, but the sigmoid function will distribute from 0 to 1. Okay, so obviously the value will be multiplied I mean, again and again, when we use a sigma activation function, obviously, even though when it comes to a ReLU, obviously it is also going to linearly like activate those values which is above 0. But in this case, we have a minus value also here for a tanh operation, because whenever we have a shoot up of the values, we will use this -1 to reduce the value somewhere like this. So why the value will be maintained from 1 to -1. So it's going to like somehow being maintained here. But when we don't use that, the value will be shoot up somewhere like this, going above 1. So that will be a major concern to be taken care of. So why we'll be using tanh as our activation function when it comes to recurrent neural network or an LSTM or a GRU, like what kind of whatsoever when you're going to deal with sequential data. Okay, so obviously we got to use a tanh activation function for sure. Okay, so one such important, I mean, ideologies of this vanishing gradient, let's say, okay, so I'm just reading this this particular review. So in this case, you can see the review stands for some Quaker oats, something like that. So it's saying like, amazing, this box of cereal gave me perfectly balanced breakfast as all the things should be. I only ate half of it, but will definitely be buying again. So when the recurrent neural network start to learn this particular sentence, to give me a comment on what is the sentiment, let's say yes or no, so whether the review is positive or negative. Okay, in this case, it will first read the value amazing. Okay, this has a great weightage, so I'll be like shooting up the gradient somewhere. Okay, and then this box of cereal is redundant for me. So obviously when I try to learn, I will forget this amazing, because it just understand the previous data alone. So when I'm here at like me or here, in this case, I will like consider only this previous data, like maybe gave or me. So slowly when I reach here, like again, I'll be like reaching this buying word alone. Okay, so obviously you can see it here. I mean, maybe we are missing some bigger point, like amazing is missed, perfectly balanced breakfast is missed, and many important words are missed. So this might lead me to the bad note. Let's say if I have a negative word here, I mean, I will not be buying. Definitely. I mean, let's say. I mean, I'm going to name a competitor cereal oats name. Let's say, I don't know the brand name. Let's say ABC brand. Okay, I will not be buying ABC brand again. So not buying ABC brand, obviously I'm having a negative word, not buying. So this was going to like make me make my neural network to reach to a different spot, right? Obviously, I mean, because it's a negative word inside, maybe the neural network will understand, okay, there's a problem there, maybe the person is actually giving some negative feedback as well. So that is where, I mean, things get messy because of not understanding the entire sequential of words. So that is where this LSTM or GRU comes into play. So where we have this memory blocks, we're going able to store down important words or important input data for the future reference. So let's say in this case, I mean, okay, sorry. So in this case, I can say that, I mean, this is very important, right? Amazing is a positive word, and perfectly balanced breakpoint is also a positive word. I don't want to use this part, this box of cereal. I know this is a box of cereal, and as you see, like as all things should be, I only ate half of it. Is also not necessary for me. So I just want to understand whether the box of cereal is good or not. So obviously, he's also recommending that you'll be buying it again. So obviously, these are the 5 to 7 to 8 words that is actually very important to my processing. So what LSTM will do is like it will store these important words in its memory block, so that it can able to give us the perfectly balanced output, I mean, for the given data. So why LSTM and GRU dominates this particular area, I mean, drastically when it comes to handling sequential data. So we will see that LSTM concept in detail. Okay, so before going into the actual implementation part. Okay, so let's say, I mean, I do have this, this is the actual fundamental block of LSTM. Okay, so this is just one LSTM block. Okay, this is one LSTM block. So where we do have, I mean, three types of gate. One is forget gate, input gate, and output gate. So this is going to be forget gate, input gate, and output gate. And this particular, area is known as cell state, which is going to be the memory lane of the particular block. Okay, so because all the past and previous data will be passing down here and there. Okay, I do have a chat. Wait, just good morning. Sorry for that. So, as I was saying, I mean, we do have a memory lane here. So where, I mean, all the data will be combined together and we'll be like deciding which data to be passed or which data to be, I mean, to be eliminated. So we'll understand this thing into detail. But before going there, I just want to show you what are all the blocks are being used for this LSTM. So the one such block, the red color block is termed to be sigmoid activation function. The blue is termed to be tan h. Okay, x is going to be pointwise multiplication. I mean, plus is going to be pointwise addition. And finally, wherever you have a merge of the vectors, I mean, merge of the two lines, it's going to be vector concatenation. Okay, so everything is very concatenate here. So likewise, I mean, we are going to use these components, okay, solely these components to build our LSTM blocks. So where we have this forget gate, input gate, and output gate. Okay, so we'll understand in much more detail. So, okay, sorry. So I'm gonna like show you the okay, maybe I can use it here itself. Yes, fine. So let's say, okay, I have a past data which is coming here. Okay, so I have the current data which is coming here. So if I feel like this past data is not important to me, okay, if I feel like this past data is not important to me, I will make this activation function sigmoid to be 0. Okay, if this becomes 0, when 0 multiplies with the past data, I'm going to have nothing here, right? So I'm going to have a nil data in this area, because since I gave it a 0, because I'm decided that, okay, this might be an important data to be considered. Okay, let me pass to the next gate so that let's see like what is actually happening. So this will forget the value. Okay, now this particular input data will cross down here. Okay, so now in this case, okay, if I feel like this particular data is very important, okay, I will be making this value to be 1, because this input data will be passed to the tan h activation function and will be waiting here. Okay, when the sigmoid is going to be 1 multiplied with the input value will reach to this particular spot, and I already forgot the value here, so we are not going to have anything here, so only the input data will be staying here. Okay, so now if this is still storing the data. Okay, this, I mean, the first gate is going to make sure whether do I need to, I mean, hold the past data or to delete the past data, and the second gate is responsible for storing the present data. Okay, storing the present data or storing the past data. Okay, and afterly, I mean, after the final gate, what it will do is like, if I decided to, I mean, make this final gate to flow, okay, flow out of the flow to the next block, what I will be doing here is like, I'll be giving it as 1 here. Okay, if I give it as 1, obviously the data will flow here. If I give it as 0, obviously 0 multiplied with this data, I mean, it's going to be giving me 0, so the data will be will not be going here. Okay, so if I give it as 1, this input data will be going here to the next block. Okay, so obviously this is going to be the memory lane. It's going to like attack to the next layers whatsoever. Okay, so this is how, I mean, we can able to understand whether this data can be stored in this particular block, or I need to push this data to the next block or so whatsoever. Okay, let's say I'm going to, I mean, let's say if I'm going to, I mean, retain that particular past data itself. In that case, I'll be giving this as 1. Okay, so this will be 0 and this will be 0. So obviously this data will not be going here at all and will not be going here at all also, right? So obviously the past data will be passing down freely to the next layer. Okay, so this is how the LSTM data or LSTM block will be used. So typically for a lot of operation, we'll be using 20 LSTM blocks or 40 LSTM block based on your necessity. We'll be like designing this number of blocks. Okay, so yes, this is how an implementation of LSTM will look like. Okay, so coming back to GRU, I mean, I'll be finishing down the theoretical part. Okay, because everything is interconnected. Without knowing those theoretical concepts, we cannot like enter into hands-on sessions. So, but yes, it's very important to know the theoretical part to, I mean, make a predicament onto the hands-on session. Okay, so we'll finish it quite fast. So maybe give me 5 to 10 minutes so that we could go for the actual implementation. So as I was saying, there's the only difference between LSTM and GRU is like the number of gates. Because in GRU, the gated recurrent unit, we do have only 2 gates, which is nothing but reset gate and update gate. Because I could say that GRU is like somehow always, I mean, not like always better, it's like somehow better for data which is lesser in size. Okay, if the data size is like less than 1 lakh or something like that, then GRU will be one of the, I mean, promising candidate to get a great output. But when you have a data set which is more than 1 lakh or 10 lakh data with you, obviously LSTM will be the right candidate to be considered. Okay, so because also you can say that GRU will be much faster than LSTM because it has lesser gates to be considered. So obviously it will take lesser time to finish this kind of a problem. So I mean, let us see like how this data is being processed here. So obviously I have past data and present data is coming here. Okay, if I decided to, I mean, keep this present data, Okay, so I mean I'm going to give it as 1 here. So the past data will be going here. Okay, no, sorry, yes, if I give it as I'll be giving this as a 0. Okay, so that the data will be, I mean, will be resetted here, because this data, the value will, okay, sorry for that, I just confused myself. So what I was trying to say is like, I mean, if I give it as 1, okay, the data will be, I mean, will be like going to this particular area. Okay, the data will also will be here, will be concatenated here, so we don't have a problem here. But anyways, when it comes to the update gate, okay, if I give it as 1, okay, if I give this particular sigmoid activation function to be 1, so 1 minus 1 is going to be giving me 0 here. So whatever data is coming here will be deleted absolutely, so we will be giving nil data here. And this data will be, I mean, this 1 will be passing down here obviously, and the present data will be multiplied with 1, and I'll be concatenating with the past data. So since the past data is nothing here, we'll be like, I mean, concatenating the nil data with the present data, so we'll be getting the present data out of here. But if I decide to, I mean, not update the present data, so I'll be giving here as 1, so that the data will be going on, and I'll be giving here as 0. So 1 and 2, I mean, anything will give me the same value, but this 0 will be like, I mean, stopping this input data to be falling down the next, I mean, block. So it's very simplified, right? So rather having 3 gates with us, it's very simple to use, I mean, 2 gates to what is it, I mean, to even manipulate the same operation which LSTM has done. So using the reset gate and update gate, it's very easy to, I mean, push things to the next level. So yes, here you can see it doesn't have a storage element. Yes, it will store the data, okay, but I mean, but not precisely like the LSTM. So I was saying that, I mean, when the data set is too high, I mean, things might get messy when it comes to recurrent unit. Okay, so we'll see these two implementation in a quite soon. Okay, but before that, we need to understand like what kind of data we are going to deal with, because these are the architecture which we have dealt right now. Okay, so architectures like LSTM, I mean, GRU have been like somehow dealt right now. But in order to use this kind of architecture, we need the data, right? So I mean, we are going to focus on, I mean, focus on to a natural language processing data. Okay, so where we have a great challenge on vectorizing the data, because obviously, I mean, computers, I mean, as is a great semantic gap between human being, where it can able to understand or like synthesize data on a numerical standpoint. But us, the human beings, doesn't want to code and doesn't need to have a numerical standpoint, because they can able to understand easily with the given context, I mean, just like that. Okay, so that's the actual, I mean, difference or the gap between human brain and the computer, I mean, processes. So in order to do that, what we need to do is like somehow we need to somehow vectorize the data set for the, I mean, for the given input. Okay, so let's say the data set contains some words like this. I need to find a way to vectorize the data. So let's say previously what people will be doing, like they'll be like vectorizing numbers, let's say I mean, keeping numbers for each and every character. Okay, so let's say I'll be giving numbers for each and every character, so that I mean, I can able to I mean, note these numbers as my translation for this word listen, so that the system can able to, I mean, take this number into consideration to learn something from that. Okay, but the problem is like when I use different words like silent and listen. Okay, so obviously the words which is the numbers which is generated, which is quite the same way, right? Because obviously, I mean, silent and listen have the same characters inside, but only the position is very different. So because of which the complexity of the entire neural network will increase, because the number representation is not unique among each other. So if it is not that unique, I mean, we might face a lot of problem in learning or like understanding the data composition. Okay, so that is where, I mean, the neural network will fail miserably when it comes to natural language processing. So currently what people are using is like they are embedding, I mean, the vectors for each and every word rather going for each and every character. So let's say I love my dog. So for I love my dog, I can give I mean, 001 for I, 002 for love, 003 for my, and 004 for dog. So I'll be having separate vector encodings for each and every word. So in this way, it's going to be little successful, obviously. So let's say I do have another sentence in the same data set. Okay, so obviously, since I have already vectorized the data, I love my, so the same number will be generated for this also. Only the new word will be added to the vocabulary set. Okay, so in the vocab set, I mean, if the new word occurs, I'm going to add a fresh number for that incrementally. So let's say 004 is the last value which I've encoded till now. So since I got a new word, I'm going to give 005 for that. Okay, so this is how the word embedding will look like. So and that is, yes, we do have other techniques to efficiently increase the accuracy, because by removing some redundant words in the data set, but we are not going to, focus on that particular part, because we are focusing on the LSTM and GRU stuffs. So obviously this, but yes, it is also better to know what kind of application, like what kind of feature extraction technique that can be done to this natural language processing, because the efficient the data set, the better the learning will be. Okay, so some things like sentence size, as well, understand like how many sentences are there, and also lemmatization is very important, because let's say, this runs and running actually the same, it is actually representing the same verb run, right? But this runner is very different, because it is indicating to a subject. So obviously what I can do is, rather having three different vectors, like let's say this is 001 for run, and 2 for runs, and 3 for running, I could combine these three word into one single word known as run. Okay, so that only one vector 001 can be given for all the names like this. So in this way, we don't have multiple competition required, because obviously it is pointing to the same verb, and then we don't want to, we just want to understand the context of it, not the grammatical part of it. So obviously which is redundant for the learning rate. So why this will help the neural network to even segregate the data, to have a unique data with it. So that is known as lemmatization. And also we do have another thing known as stop words. So stop words, something is like is, was, that. So these are the redundant words, but doesn't contribute anything to the meaning of the particular sentence. Yes, it also contribute to the tense of the sentence, but we don't, define sentences. Tense of it, unless sentence is very important. So in order to, because since these are redundant, okay, so I don't want to, keep in my vocab set, so I can directly remove those stop words just like that. So let's say, I am a good boy. So you can see that I am, is not an important word to me. So okay, only important words are like I is an important word, good is an important word, and boy is an important word. So it says something is good, he is good, something like that. So we can able to understand the context of the sentence without having a proper grammar, right? So I good. So if I say I good, even you can understand, okay, I am good. So that is also, the technique which is being followed here, so that lesser vectorization, lesser number of vocab set, greater the learning, greater the, learning will be occurred for this neural network. So okay, that's other things which you need to take care. And also we can also recognize the parts of speech, dependency parsing, even word work is very important, because we'll be converting all the vectors into 64-bit or 30-bit encoded values. So even that will be very unique, because the neural network are always data hungry. So when we pushed on good data and large amount of data, we can able to get a great output out of that. Okay, so these are the some of the techniques which can be used to increase your accuracy, because at certain point of time we might be not getting a great output because of the data set, which might be little bad. So we need to use this kind of feature engineering techniques to somehow increase the accuracy. So this is still the theoretical part. Okay, so do we have any other doubts till here before we proceed to the hands-on session? Any other doubts which has to be clarified? Okay, so uh, I believe that there are no other doubts. So I believe that we'll be getting a lot of ideas when we are actually visualizing the same theoretical concept in the hands-on session. So let us go to the Google Colab as usual. Okay, so the entire implementation done using Google Colab. So if you're not habituated, just get habituated, because it's one of the greatest IDEs you can get with a free workstation with a great processor like 16 GB graphics card with for free. So obviously it's like a great gift for a lot of people who doesn't have great resources in their laptops. So all you want to do is go to Google Colab and search my repository Deepan Raj M. Okay, so this is going to be my repository Deepan Raj M. So once you search that, okay, so it will be showing multiple repositories, inside which go for deep learning. So Deepan Raj / deep learning. So okay, go to that repository. So inside which we have a lot of models here. Okay, a lot of programs. Feel free to use all the programs which I have in my repository. Yes. So I'm going to call this NLP slash NLP.ipython notebook, because initially we are not going to, we are going to somehow extract the features, like vectorize the data before going into the actual recurrent neural network concepts. Okay, so we're going to vectorize the data set for firstly. Okay, so this will help us to understand like how this vectorization is actually happening and what are the important steps to be taken care before you handle out your stuffs to the neural network. Okay, so let's say, for this particular thing to happen, we are going to use TensorFlow. Okay, TensorFlow, you are what to say, uh, TensorFlow library. Okay, so we're going to use TensorFlow library to do this particular operation. So in this case, I'm just creating a sentence here. Okay, so I have 4 sentences here. One is I love my dog, I love my cat, you love my dog, do you think my dog is amazing? So using these 4 sentences, I'm going to create a vocabulary set for the same. So in order to do that vocabulary set, so I'm just want to initialize this particular tokenizer function into an object tokenizer. So this particular variable will become an object once we initialize this particular function. Okay, so once that is done, I'm going to use this object. I'm going to call an attribute fit on text on all the sentences. Okay, so throughout all the sentences, I'm going to use this attribute fit on text. Okay, so once the fit on text is happened, okay, this can able to give me the word index for each and every sentence by using the attribute word index. Okay, so once it has got the hands on the sentences, it will understand what are the unique data which we have. So once the unique data is found, we will be using this tokenized word index attribute to get the entire word index for each and every word. So let's say I'm going to run this particular part. So it might take a little bit of time to connect to a virtual system which will be anywhere in the world. Okay, so that's connected. So now you can see that these are the unique words which is available in the entire sentences. So let's say I have 3 my, right? So but for only one word is given here. So for my it is 1, for love it is 2, dog 3, 4, 5, 6, 7, 8, 9, 10. So we do have 10 unique data in our sentence. So this is nothing but the vocab set. Okay, so this is the vocab set which we'll be using for the entire learning process. Okay, uh, and then yes, with the vocabulary set, we'll be like padding down the sequence, because everything should be in the form of sequence. So we cannot like pass on one by one word. So for each and every sentence, we need to form a sequences for it. So once again, yeah. So sorry. So let's say I'm just using the same sentence here. Okay, so that's done. And now I am just introducing another attribute, another parameter in the tokenizer function, where it's nothing but OOV token. So OOV stands for out of vector. So let's say okay, let's say I have a test data. In that test data I have a different word, okay, which is not at all inside my vocabulary set. So in that case, my entire model will crash apart, because it cannot able to understand what data it is, and doesn't have a word index which is mapped to that. Because of that, we will be having a very big problem. So in order to reduce that, in order to somehow eliminate that, we have a concept known as out of vector. So whenever we have an unknown element, whenever we have an unknown data which is not inside the vocab set, that will be considered as 1. Okay, so the word which is not inside the vocab set will be considered as 1. But if the word is already considered inside the vocab set, then the same number will be given to it. Okay, so that's also another important thing to be taken care of. So OOV is also been given in the parameter part. Oops, sorry. And then I'm just fitting on the sentences, and I'm going to generate the word index. And then what I'm going to do is I'm going to find the sequences for it. Okay, by using the text to sequences. Okay, so I can able to create a sequence for it. Let's say I have a word like I love my dog, right? So for this I love my dog, you could see you know that oops, like my is 1, for I is 4. Okay, 4, and love will be 2, my is going to be 1, and dog is going to be 3. So it's going to be 4, uh, 2, 1 and 3. Okay, so this is going to be the word sequence for the particular sentence. Okay, so that's what I'm trying to do here. Okay, so using text to sequences, it is going to convert that entire sentence into sequence of numbers, which will be taken from the vocab set. Okay, and then I can even pad the sequences, because we know that neural network will accept only a fixed number of input. Okay, if it is having a different data set size, different data size, obviously it will throw me an error, because if we like integrate, like let's say I have only input neurons that I can able to accept only 5 data, maybe like 5 neurons is like given to the input layer, obviously it can able to accept only 5 data. If I have 6 data with it, obviously the neuron will the entire neural network will throw me an error, because I have I have an extra data with me, and I don't like how to process that. So that is very important to be considered. So we'll be like giving some padding operation to that, so that if the sentence is like bigger than 5, okay, we'll be reducing the sentence by cutting down the words. Okay, if the sentence is less, we'll be appending zeros to it. Okay, so I've given like max length to be 5. Okay, so let us run this part and see like what are the things that are happening actually. So as usual, we have the word index, but here in this case, you can see the word index have been increased to extra number, because since this OOV has come into play, okay, that is going to be 1. Okay, so always OOV will be decided to be 1. Okay, so now you can see this is the sequence. This is the sequence without padding. Okay, so we have 5324, 5327, 6324, and a very big sentence like 8692, 410, 11. So now when I try to pad it up, if I don't give any value here, it's going to be pre-padding. So the data will be padded in the pre-condition. Okay, so let's say I have only 4 words, 4 numbers. I'm going to pre-add the zeros in the all the sequences. But in this last case, since I have more numbers than 5, I'll be like in padding down, I'll be like striking down this 8 and 6. Okay, since making sure only the 5 data is available. So 9, 2, 4, 10, 11 will be available. That's it. Okay, so this is very important, because we need to maintain the number of words or number of data which is available when we push to a neural network. Okay, so and then now let us try to fit the test data. Okay, let us try to create a sequence for test data, and let's see what is happening. So you can see I really don't love my dog. So obviously really is not there, right? And also my loves is not there, because since haven't used this lemmatization, love and loves have a different word. House is different, and much is not. It's also not in the vocab set. So now when I run this particular part, okay, and yes, I have made sure the max length is going to be 10, and the padding is going to be pre. Okay, so even I can mention that if I don't even mention that, obviously pre padding is going to be padding is going to be pre. Okay, so this is the text sequence, and this is the padded sequence. Here you can see the test sequence. For really it has given it as 1, because it is like out of vector, out of the vocab set, so it is giving it as 1. Likewise, loves is very different from the vocab set, so it's giving 1, and house and much is also different, so it's going to give me 1 and 1. Okay, so if I decide to go for post padding, I can also do that. So all the zeros can be appended at the last stage, because it's up to us to decide whether to do pre-padding or post-padding. But on a default node, it is always going to go for a pre-padding. So this is how we do tokenize the data which is given to us. So this is the feature engineering which you're doing to make sure all this data can be like ready to deploy to the neural network. So do we have any other doubts in this particular part? Yes, Sendil sir. So I didn't saw your chat. Sorry for that. I want to use dashboard. How can I integrate Collab or Jupyter Notebook? So it's nothing, sir. You can just go to Collab. Okay, you can just type Google Collab. Okay, if you have your Google account, you can directly use your program. So we have this Google Drive with us. We have a GitHub repository part. Even you can upload an IPython notebook directly to this Google Colab, and you can run it. So even you can save the contents into your Google Drive. But if you feel like you want to push some data, let's say I'm just pushing all my programs to GitHub. From GitHub, I'm just pushing down to the Colab. So it will like neutrally can be accessed by anyone. So there are like multiple options there. You can even create a new notebook here and type your codes and whatsoever, and you can even save the notebook in your local Google Drive, and even you can download this IPython notebook to your local directory as well. So that's up to you, sir, to decide on which on how to do it. So it has all the capabilities to do it, so it's up to us to proceed on which direction, sir. Okay, so great, thanks ma'am, thank you. So we'll go for the next part. So let me open another program that has a data set with it, and also the LSTM implementation. Okay, so before going into the LSTM implementation, let me show you the data set first. Okay, so yes, I'm gonna copy this part. So this is the data set. Okay, so I mean this data set is all about sarcastic data set. Okay, sarcastic headlines will be there, and the output will be whether the headline is sarcastic or not. Okay, let's say I mean let me take a word around here. Okay, what is that? Yes, stock analyst confused, frightened by a boar market. So obviously it is not actually representing the actual news, but is sarcastically like saying some other thing inside it. Okay, so it is like making us to understand. Okay, I mean jokingly like I mean giving us a news. So obviously it is sarcastic. So understanding a sarcastic meaning is very difficult even for human beings because we need to be in the right form. So we are going to use a difficult data set as you can see it here. Okay, so because since it is a news headline, the vocabulary set will also be very higher, right? Because I mean we'll be having different words to be considered. So yes, we do have another attribute like article link. So we will not be using this article link at all. We'll be using only the headline and the output sarcastic or not. Okay, so this is the data set which you're going to deal with. Okay, so yes, so we are gonna first we are gonna download this particular data set to our local drive here. Okay, so once it is downloaded, I'm going to because since it is a JSON file, I'm going to load the particular JSON file, and then I'm going to append all the sentences into the sentence list, all the labels into label list, and all the URL into URL list. Okay, so I do have three arrays like three lists here. So I'm going to use the sentence and labels just like that because I don't want the article link at all, because it's not required for me. So I just decided to, but making sure I even append this article link for a safer purpose. If it is needed, we can use it. So anyways, I have loaded the data set, and I have updated, I have like what is it? I have appended all the sentences. Inside of the data set into the sentence list and to the labels list. Okay, so that is done, and then as usual, we know that we are going to utilize this. TensorFlow's tokenizer and pad sequence functions to tokenize those words and to pad it out. Okay, so let's say in this case, everything is going to be the same till here, right? But in patch sequences, you can see surprisingly, I didn't give any max length. So if I don't give any max length to it, it will automatically take an average of the particular sentences available, and based on it, it will give me an average padded value. Okay, and I'm going to explicitly mention as post padding. Okay, so to see like how it is happening there. So let me run this particular part. But before going there, we need to do a small precondition where we need to uninstall TensorFlow and Keras, because the implementation which I've done is in TensorFlow 1.14, but in TensorFlow 2 there are like different different implementations happening. Few functions have been made different. So why this code will not work in TensorFlow 2.0, because there is one bigger problem in Collab, because automatically it will be getting updated to the latest version. So I'm going to install TensorFlow 1.14 and Keras 2.1.2. Okay, so I just made sure I just uninstall this particular part and install this Keras and TensorFlow with this particular version. So if you're going to use my program, sirs and ma'am, just make sure that you are installing this particular part. So yes, we need to install GPU part, TensorFlow-GPU, so that the GPU version will be installed. Yeah, it is downloading the data set. Sorry, it is like downloading the TensorFlow library. Sorry, I misconfused it. That's like totally 380 MB. So it's installing the package for now as we speak. So even if you are going to, if you are implemented a particular operation in a different version of libraries, you could always uninstall and install using this kind of an operation. Okay, so but making sure that before you import the libraries, you do uninstall and install, because you need to otherwise you need to restart the runtime again to execute the programs. Okay, so I made sure that I've done this particular part in the beginning of the beginning of the code before I import this libraries. So I'm gonna run this particular part. So obviously this duplicate function will be downloading the data set here. You can see sarcasm jot JSON file is downloaded, and I do even upload all the contents here. So this is how the data set is look like. So you can see, I do have 29,657 unique data. So those many numbers of data have been entered into the vocab set. So you can see the vocab set is like going like this. So 29,657 new data. Okay, so obviously it is one of the biggest vocabulary set which you can ever get, right? So obviously it's like very very big. And as you see here, since I give the max length is taken as 40, because based on the number of words in the sentence and an average note, it has taken 40. And then it is it is uploaded all the sentences into some parrot sequence, something like this. So I'm just visualizing one of the parrot sequence here. Okay, so you can see print parrot of 0, that's going to give me that, and print parrot of shape, because parrot shape is very important, because we need to understand how many vectors have been used. So in this case 40 feature vectors have been used, so that I need to use 40 input neurons to get this data to inside the neural network. Okay, so till this, okay, it's fine. Now we are going to go to the actual neural network part. I guess it is like pretty straightforward here. So the only new part which you're going to see here is like the embedding of the layers and the LSTM. Okay, because these two are pretty known to you when you have done this multi-layer perceptron and other stuffs. Obviously sequential and LSTM, the dense layers will be used, right? So I'm going to import all these layers now, and then I'm going to create a sequential model. Okay, that the object is created on the sequential model, and I'm going to add a layer of a neural network where it's going to have the input layer is going to be 40. And this too is very important here, because I'm going to embed this entire data into 64-bit format. Okay, 64-bit format is going to be the embedding input. Okay, so output is going to be 64, so it can able to accept 30,000 data. At the given shot, because I do have only 26,709 data with me. But anyways, on a rounder node, I just given it as 30,000 data, so I can able to accept 30,000 data and converting all the each and every individual data to be 64-bit encoding format. Okay, and I've also dropped out 20% of data, because I know that the data set size is huge. Okay, because we might have redundant words, a lot of redundant words here and there, so I'm just decided to go for dropout to be 0.2 percentage. And then I'm adding 40 LSTM blocks here. Okay, since I have 40 feature vectors here, I decided to go for 40 LSTM blocks here. Okay, so 40 LSTM blocks is given, and that's it. And finally I'm going to give an output neuron, okay, which is going to be 1, because it's going to be it's a binary classification. It's going to be yes or no. So I decided to go for 1 neuron. Init is going to be uniform, activation is going to be sigma, because this is for an output. But you might be asking why we didn't use tan-h, because we are not going to pass. This is not going to be an intermediate layer. This is going to be the output layer, where the neuron should give either 0 or 1, because 0 represent one class and 1 represent another class. Okay, so that is how this that is how this activation function will work. I believe that you know about that. So I've used activation function to be sigmoid for the output layer. Okay, oops. So I'm going to create this architecture, and then I'm going to use loss function to be binary cross entropy. Optimizer is going to be Adam. Matrix is going to be accuracy. I'm going to deal with 10 epoch. Okay, so let us go for 10 epoch, because yes, obviously we can go for multiple epochs, but it might take more time to train onto it. So I decided to go for 10 epochs for now, and batch size is going to be 100. Okay, so now let me train it out. So here you can see, even though I'm utilizing this GPU with me, it is taking a lot of time to do. A lot of time to train onto it. But you can see suddenly, the first epoch I got 67%, but the next epoch it is like even grown much better. Yeah, the accuracy is like slowly growing as we see right now. So, and also while it is being trained, I will show you another program which where I've implemented the same operation but using multi-layer perceptron. Rather going for LSTM, I have done using multi-layer perceptron. So everything is going to be the same here. Okay, there is no much of a difference. But let me uninstall the package first. So everything is going to be the same here. Okay, I'm going to run this part. I mean, all the things going to spin. Only thing is like I've implemented a normal multi-layer perceptron here, where I will be having input dimension to be 40. Immediate hidden layer is going to have 40 neurons. Activation is going to be ReLU. And the second hidden layer is going to have 20 neurons. Unit is going to be uniform. Activation is going to be ReLU. And the final dense layer is going to have only one neuron because that's going to be the output. The activation function is going to be sigmoid. Okay, so everything is going to be the same. And I'm going to I decided to go for a epoch to be 200 because I know that I mean, even at 200 epoch, we not be getting a good output because this is not going to handle sequential data, right? Because this since is multi-layer perceptron, it's going to handle all the data in the present node, not in the past or the I mean sequential node. Okay, so let this also run. And let us compare with these two operations, obviously. But I'm pretty sure that by the time it is running, we might be I mean we might even finish this training part here because it will be running fast because each and every epoch is taking just I mean less than a second. Okay, but in this case each and every epoch is taking 18 seconds to run because you know that we have 3 gates in LSTM and we have 40 such blocks. So all the 40 such blocks have to be I mean have to update, have to delete, have to like push down the data. It's a tedious and a very big process. So as you can see, even for a I mean even for a 10 epoch, it is taking this much amount of time, right? So obviously, if I but anyways, it's better to go for 100 epochs so that more the epoch, better it can able to learn. But yes, we can't go for 1,000 epoch because obviously there'll be like no learning at all. It might stuck into a local minima somewhere around there, and beyond that it will never learn at all. So it's always better to go for 100 epoch and see like how is the learning rate for each and every epoch. If there is a significant I mean increase in the accuracy even after 100 epoch, then we can even go for 200 epochs. Okay, so that's up to us to decide. So now the 10 epoch training is done. Let us calculate the accuracy for it. Okay, the accuracy which we got is 97.85 percentage. Okay, it's pretty good, right? So it's a decent output, which I can say, because when for a sarcastic data set, it is even a tough challenge for human beings to understand whether the given, I mean, title is sarcastic or not. Because you know the accidental, I mean, news which was generated. I mean, not ever generated. I mean, people misconstrued when Donald Trump said that we have to inject this sanitizer into our body so that it can kill corona. He was actually jokingly saying that, but lot of news channel accusated that Donald Trump is fool who is trying to jeopardize the entire world. But actually he just done that on a sarcastic note. But people, a lot of news reporter found that not sarcastic, and they treated it as a serious news. So that's the problem in sarcastic news. But anyways, you can see no matter what I do here, okay, it's okay. You can see the learning rate would have been stopped even right before this. Yeah, maybe the learning rate can be here somewhere. Yes, even at 100 epoch itself, the learning rates have stopped because it is not going more than that. Okay, it's like somehow fluctuating here and there. Okay, somehow it has reached to 64 percentage. So the maximum accuracy which you can get for a multi-layer perceptron for a sequential data like this, it's 64 percentage. So obviously it doesn't handle past data with it, so we are getting a bad output. But RNN, the LSTM concept came into play and help us to get a great accuracy of 97 percentage. So now let us even try to run the same program for gated recurrent unit, because I know that gated recurrent unit can even give me a better output than the LSTM, because since the data set size is less than a lakh, so obviously this will be the right candidate to do it out. Anyways, I need to uninstall the packages as we speak, and then I need to install the package. Pip install TensorFlow 1.14 and Keras 2.1.2. Okay, so everything is going to be the same here, so there is no much of a difference. The only difference which we have is like the GRU layer. Okay, maybe to keep things on a common note, I'm going to go for 40 GRU units as I did for this your LSTM block as well. Okay, so I'm going to go for 40 GRU units and everything is going to be the same. Oops. Okay. Uh-huh. Sorry. I used the knob install. Okay. I just use the wrong word. Let it install. Installations on progress. I take, yes, it is done. So next, let me go to the bottom of it. So yes, let me run this particular part. Yes, it is done. And then I'm going to run this particular part. I'm going to run this part. So, oops, I just, okay, stop it. Because I need to keep 10 epochs here. Okay, because everything should be the same. Let's see, like, so that we can able to compare. I mean, the accuracy of GRU and LSTM, because obviously, as per the charts, GRU should work better than LSTM, because it is always better in handling lesser data. Okay, so but you can see like drastically the accuracy is increasing even the first epoch, right? Because in LSTM we got an accuracy of 67% in the first epoch, but in GRU we are getting close to 80% as an accuracy. uh, yeah, more than 80%, right? 81% as an accuracy in the first epoch itself. So obviously it's like giving us a great output as we speak. So this is one such implementation where we can able to use gated recurrent unit and LSTM to mitigate a sequential problem. It's like many to one operation because it's a sentimental analysis output. So where we have many to one output, where we have multiple words and one output, whether it is yes or no, or like whether the given the sentence is sarcastic or not. Okay, so okay, I believe that we have a clean competitor, we have a clean winner here, right? Because in the third epoch, we have got an accuracy which is close to 97. So obviously it might reach 100% or even 99% in the upcoming epochs for sure. But I can guaranteely say that it is way more better than this 97.85. I mean accuracy for LSTM. But let's see what is actually happening. Yeah, we have a clear winner here. So okay, let it run for some more time because it will takes quite a long time. So before it goes there, we could even understand the other concepts which was intended to take in this particular session. So, yes. Okay. The next thing which I was planning to share is this attention model. Because even though when we use this LSTM and GRO and other stuff, attention model termed to be one of the best, thing when it comes to, a huge data set. So this is one such implementation where the author, this implementation is actually done by Facebook. Actually, this architecture, right? So what this attention model is do, like, we'll be having three data here. One is going to be sentence, another is going to be question, the third is going to be answer. So based on the sentence and the question, my neural network should say whether yes or no. Let's say yes or no for that particular question. Okay, let's say I'll be having question like Sandra went to shop, she got milk. So I'll be asking question like whether she got milk. So the answer should be yes or no. Okay, so that should be the output for this particular attention model. Yes, we can even do a lot of great stuff using attention model, because attention model is a concept where a lot of attention will be given for repetitive words. Okay, if a repetitive word is coming again and again in the particular training process, more importance will be given to that particular words, so that it drastically improves the accuracy of it. Okay, even better than the attention model and the GRU. Okay, so in this note, I'll just walk you through this architecture here. Okay, the same implementation is done in the programmable part. So once we find this easy, it's easy to go to the implementation part. So the implementation which I've done is like we have a question here and we have sentence here, and this is going to be the particular answer. Okay, so obviously what we're going to do is we're going to embed this question. Okay, and we're going to keep it here, and we're going to embed the sentence and we're going to keep it here, and we're going to do this cross product. Okay, this dot product, inner product with this two, embedding A and embedding B, and we'll be getting an output for that. And once that is done, we'll be using the softmax classifier to somehow activate the important weights and important output from this particular data, and that particular data will be embedded again with another embedding C. Okay, this output of the softmax will be concatenated with the another embedding of the sentence. Okay, and we'll be taking a weighted sum of this particular output, and we'll be giving it to the we'll be summating again with the question to get the particular answer. So why we are doing it for two times? Okay, why we are pushing the sentence for two times is like this particular part is the actual heart of this attention model, because I'm going to look for relevant answers. Let's say Sandra got a milk. Okay, so the sentence is like, if Sandra got milk. So question is like, okay, I'm sorry, I mean, let's say the sentence is like, Sandra went to a mall, she got milk. Okay, she got milk. So the question will be, did Sandra got milk? So obviously I do have two words here, got milk, and got milk is actually available in the sentence and also into the question standpoint. So obviously this maybe got milk is going to be very important to me, because this might be a crucial thing to answer it out. So with this embedding will make sure that the important data which is actually repeated in the sentence and question will be like given us more attention, so that, and finally we'll be embedding with the entire sentences, so that the desired output will be like yes or no, for the same. Okay, so this is just one block. Okay, this is just one block here. So the same will be happening for iterations. Okay, so 3 iterations will be happening again and again and again to get the predicted answer. Okay, so but for in this note, I couldn't able to go for three iteration, because even for one iteration itself it is taking a long time to train. So I decided to stop with the one block. Okay, so my implementation will be like this, nothing will be here. So output will be startly going like this. So okay, like this part, this is the actual implementation which I've done, since I don't have the liberty of, because obviously Facebook has a great server with them, so they can run this like a finger of a snap. Snap of your finger. Sorry for the wrongest idiom. So but in this case, since we are using Google Colab and we don't have a powerful processor with that, I'm not going to go for multiple iteration of this particular same attention model. Okay, so by the time I guess this would have been finished. Yes, you can see at some point it has reached 1% accuracy, right? So obviously we have reached 100% accuracy in GRU. Okay, so that is the beauty of GRU, guys. So obviously LSTM can able to give us a great output, but yes, when your data set is less than a lakh, obviously it is always better. Straightforward you can go for a GRU based unit. So but surprisingly the time required for LSTM is 19 seconds, but the GRU took 30 seconds, which is surprisingly shocking to me. Maybe it might be a load, a huge load for the to the particular server, so that it's taking a little more time. But as per the theoretical part, it should be faster than the LSTM architecture. Okay, so that's one thing which you need to take care. So I'm going to terminate all the sessions, because we do have a lot of sessions, I guess, running around there, that is making things a little slower. So I'm going to terminate everything. Okay, so now all the sessions are terminated. You can straight away go for the attention model, just like that. So let us go for the attention model. Okay, so yes, here it is. Yes, so I'm not going to go into detail about this program. So I'm just going to give you a gist of it. But anyways, before that, we need to uninstall Keras, then install. Okay, so in this case, what I'm going to do is I'm going to clone the repository first, so that I can push the dataset to my particular uh, so what is happening is like why am I cloning this repository? It's like I have stored the dataset inside my GitHub account itself. I will show you that in the meantime. Yes, go inside deep learning attention model. So this is the actual dataset. Test dataset and train dataset separately is available to me. So I'm just cloning that so that I can take the test and train data. You can see this is where I've stored here. So once the GitHub repository is cloned, okay, everything will be like given here, so that we can access the data somewhere inside. So let it finish. Okay, it's taking a little bit of time to install the package. Yes, you can see the entire dataset, entire GitHub repository will be cloned. it is not yet finished yet. Yes, now you can see the contents here. Inside attention model, I have the data set with me. So that's what I'm doing here. So I'm just loading this trained data set and the test data set, and I'm loading everything into the trained data and to the test data label. Okay. So once that is done, let me show you the length of the training instance. So I have 10,000 training instance and 1,000 test instance. So let us see one instance of the data, how it will be. So this is the actual data set. Okay, this is one such instance of a data set. Okay, likewise, we have multiple data. So we can see it elaborately. So this is like a sentence to me. Okay, this is a sentence, and this is going to be the question. Okay, and this is going to be the answer. So we have a sentence, question, and answer. So you can see Sandra went back to the hallway. Sandra moved to the office. Is Sandra in the office? Obviously, Sandra is in office. I'm going to give the yes as an answer. So, and finally, I'm going to add everything to my vocabulary set, and I also make sure that this yes and no is also added to my vocabulary set. Okay, so that is also being taken care. And let's see how many vocabs do we have here. So surprisingly, you can see it for 10,000 instances, we have very less data, right? Very less vocab set. Because Facebook have intelligently made only 38, 37 vocab, 37 unique words in the entire sequences which they have used in the entire 10,000 sequences. But in the previous example for 30,000, we did have 29,000 unique words, right? So the vocab set is very higher than the number of instances, but in this case, it is cleanly maintained. The cleanly created data set is available for us. So I'm going to combine all the data together. So I'm going to say the entire story length, max story length, and a max question length to use it for my vectorization. So vectorization it's very straightforward to us, right? Because we know what we're doing here. We are just converting the data into vector and padding the sequences for each and everything, for x, for question, and the answer. X is going to be the sentence, x is going to be the question, and y is going to be the answer. So let me run this right away. So the entire vectorization block, and then building the neural network. So yes, sorry, oops. Oops. I think that this particular model is utilizing this. Give me 1 second. Additions of max. Batch size. Shit. Okay. I actually I implemented this particular thing with TensorFlow latest version actually. Sorry for that. So and I wanted to install this versions again to the latest version install because I have recently created this program. Okay, sorry. Sorry for the trouble caused. Now I need to install the latest version of the package because this program I have migrated from the old version to the newer version. So sorry for it. Now I can show you once I import the TensorFlow with the older version. Now I'm installing the new version, right? So I need to restart the runtime. So that's for sure. Just installing the package as we speak right now. Okay. So I need to restart the runtime so that all the data will be refreshed because we have already imported that particular library with us, right? So we are making sure it is loading again. So from here, I'm going to run, after. Okay, so everything is going to run. Yes, as I was saying, vectorization is very simple. So, so in the building networks, it also everything is going to be the same, but we are just implementing here just like that. So here you can see I'm just encoding. I'm creating an encoding for one set, another encoding for the the sentence and the question, and then I'm creating a a question encoder here. Okay, so this is input encoder. This is another input encoder. Two input encoder will be there for sentence, right? So that's happening, and question encoder is also created. Now I'm going to create this. I mean the encoded value into sequences, and I'm going to use a dot product, and activation function is going to be softmax, which is as same as your I mean architecture, and then I'm going to permute that, and then I'm going to concurrent with the question encode with the response, and finally I'm going to an LSTM layer where because I need to store some important data which is being attended. Attention data will be stored in the LSTM layer, and then I'm going to drop out, and I'm going to like create a final output model. Okay, so and while training, you can see I've just decided to go for 10 epochs here. Okay, but 10 epochs will never give me a good output, obviously, because you can see the validation accuracy is 50 percentage. But yes, I have saved the data into a model file, and I'm loading the weights again, and I'm going to predict the data. Okay, I'm going to give some sentences, some test data. So you can see for this particular test data, Mary got the milk there. John moved to the bedroom. John is in the kitchen? So the answer should be no. The predicted answer is yes. It is absolutely wrong. Okay, it should be no actually, but it is given as wrong because I know that I have just ran for 10 epoch, but if I ran it for 200 epoch or more than that, obviously I might have a good learning because you can see the accuracy here is just 54% probability. Next question which I've asked here is like Sandra picked up the milk, Mary left, Mary traveled left. My question is going to be like Sandra got the milk. The answer should be yes. Yes, I mean we have got a partial answer of yes, but anyways I can't rely on this answer because I just got 50% of accuracy, which is pretty bad. Okay, but if I run the same model for 100 epoch, let's at least for 100 epoch, definitely we might even get a good accuracy because you can see it's like the accuracy is slowly increasing because since the dataset understanding is little tedious, it's always better to go for more and more epochs. So this is just one such implementation of attention model, and the same can be applied for this text generation as well, because let's say till now we were like understanding this attention model like yes or no and even sentimental analysis, but let's say if you want to generate a text, all we need to do is push this as my input and predict this as my output. That's it. So the input is going to be hello, let's say, and the actual output should be oh. Okay, so I'm going to push this as my training data to my neural network. Okay, my neural network will understand this particular data and will try to form the predict the actual intermediary character. Okay, so I'm going to compound this character and with this character and see whether I've generated rightly or wrong. If it is right, the weights will be updated to a lesser point. If it is wrong, the weights will be updated accurately. Okay. Likewise, I'll be slowly, this text generation can be like slowly learned again and again and again to form a perfect text for us. So I can show you the path of it, because we have a very less time here because I already reached the intended time. So I can show you here. Okay, so the dataset which I'm using is like the Sherlock Holmes book actually. So one book is formed into a text file. So this is going to be my training data. Okay, so I'm going to use the data here. You can see, sequence length is going to be 40. The next data, the 41st character is going to be the predicted value. Okay, so this is going to be my input. The 41st data is going to be my output. Okay, so let me run everything by the time I talk about it. So and also like you can see, like I'm converting those vectorization and all the stuff is happening here, and finally this is where I generate the things. Okay, so what I do is like I will push this 40 data. Okay, I've just created a seed here. Okay, I'm going to push this as my test data. Okay, after this my new character will be generated based on the seed. Okay, by the time of training. Okay, so obviously it will predict one single word, and that word will be appended to the entire seed text. So in the seed text, that word will be appended. Slowly the word will be appended again and again and again to get the entire text. So I'm going to go for 1000 iterations here. Okay, so you can see it for seed here, like 1000 iterations, so that 1000 characters will be created for one such generate new text function. So in this case everything is going to be the same. Okay, the only difference which I've made is like this callback function. Okay, so here in this case I have in this model.fit we have a function known as callback, because this training will take a long time to train, so that I have done a callback function, so that after end of each epoch I will be executing this output one time to see like how the text is being generated. Okay, likewise for each and every epoch I'll be running again and again, executing the output again and again to see like how better my model is actually being trained. So it's very simple in the implementation standpoint, because the basic idea is like we are going to predict the next character rather having next word. We are going to predict the next character, and since we have a very big data set with us, because the entire Sherlock Holmes books is there, so obviously my neural network is going to be trained onto that particular book and is going to become a great author by oops, it's waiting for yes shit. Okay, so it's going to become it's going to like create a great story, I mean, after some many epochs, because obviously it's not going to, I mean, generate good amount of story just one or two epochs. It should at least need like what to say, like maybe minimum of 200 epochs, let's say. Okay, it got stuck at some point. Yes. Okay, I didn't saw this coming, so let it run. Maybe I can wait for the execution of one epoch alone, and let's see like what is actually happening there. Yes. Everything is running. This might go a little fast, but training part, you can see for one epoch it will take a long time to do it. It will take 1 minute precisely for one epoch. So this will take time because the dataset size is very big, and aggressively I'm just predicting the words. For every 40 words, I'm just predicting the 41st word. So likewise, it has to be trained, right? So I can show you the generated text after one epoch. So yes, it is a very useful function, right? Callback function will be very useful for a neural network. So it's not going to be used for only RNN. You can use it for any other purpose to immediately see the output after each and every epoch. Running. Okay. So all the codes are available in my GitHub repository, github.com/deepanrajam. You can go to my repository by even going here and searching between different repositories which you want. Okay, so even you can see the attention model is still running, but you can see the accuracy is like drastically increased to 85%, right? So that's what I'm trying to say. So we will be getting even a great output, I mean, when we go for more and more epochs. But in this case, you can see even it is still running for one epoch. That's the uh, so that is what is happening here. Okay, let's wait for a few more minutes till the time it is being done. Sorry for dragging your time into this, but anyways, I just want to show you this output so that I'll become satisfied. I guess we could even see the output for this attention model, I believe, by the time it is being trained here. Let's see what happens. Maybe I could even go for more epochs, I believe, because it's like slowly increasing, right? The accuracy is like slowly increasing. Even maybe 200 epochs might be useful. I mean, might be useful, I believe. So now let's see the output. Now it is giving me the right output, right? Because I've trained it, I mean, nicely here for 100 epochs, but even I can go for more epochs also, and I've got a right output, and the prediction probability is 99%. So it's very precise that it is very confident that this is the output. Likewise for this particular thing, does given the right output, yes, this is the right output, and we have even got a 96% of probability. So that's what I'm trying to say. So more the epoch, better the learning. But yes, if we can't go more than like 1,000 epoch, obviously learning rate will not be there. We should constantly maintain this, I mean, accuracy chart to see like whether it's actually growing or not. Okay, so yes, finally we have done for one epoch here. You can see this is the generated text. I know this is very bad. We don't have a meaningful word at all here because it is just only now only it is learning. But you can see some words are rightly formed here, like in, right? In is formed right, and then okay, nothing else is formed rightly here. Only one word is formed correctly. So after epoch by epoch by epoch, this will slowly gain its knowledge on how to write the words, how to calculate the, I mean, how to predict the words for it, so that I mean, we'll be even getting a great output for it. Okay, so this is the actual implementation which I'm trying to see. So that's it from my end. Do we have any other doubts to be clarified?
போலாமா?
Sir.
Yeah, ma'am. Fine.
Yeah, thank you all. On behalf of Sri Krishna College of Engineering and Technology and the entire fraternity of the college, first of all, extend a very hearty vote of thanks to our speaker who spared his busy schedule to grace the occasion. Once again, I would like to thank our distinguished speaker, Mr. Deepan Raj, for making an excellent and enlightening presentation and making this FDP a very meaningful and interesting. I hope this session oriented the participants for a technology-rich future and keeps up the change by adopting effective strategies. Thank you all.
Thank you, ma'am.
Thank you, sir.
Thank you everyone for the opportunity. Thank you.
Thank you, sir.
Thank you. Thank you, sir. Thank you so much. Bye-bye.
Okay, sir. Dear participants, the next session will be started on 11:30. So we will meet again. Thank you. Upala ma'am, stop the recording.
Okay, sir.